Okay, so we're going to pick up rather where we left off last time. And so just quick little recall from what we were discussing towards the end of our last class is there are two main components of neural network architecture. The first are the layers and nodes. So in some sense, kind of a big, like a geometrically, what does the network look like? How many layers are there? How many nodes are there at each of the layers, etc. Okay. So it's kind of the physical structure, so to speak, of the network. And then the second component, which really adds a lot of the sort of flexibility and kind of variety to the way the neural network behaves, is the choices of the activation functions. Now, as we'll see, of course, there's more to a neural network than this. There's the actual sort of algorithmic aspects, but these are basically the kind of, if you think about it as sort of like a physical network, these are the physical components. They're the various kind of locations, and you can think of the activation functions almost like, I don't know, if you think of a neural network as sort of as a network of, say, places and then connections, roads or something between them, the activation functions in some sense are like the traffic signals that dictate how, well, in this case, information flows through the network. Right? So there's a bit of a strained analogy, but anyway. So last time we talked about layers and nodes, and today we're going to spend the whole day talking about activation functions. There's much more to say here than there was about the layers and nodes part. Because there's lots of choices that can be made. All right, so in a perceptron, so in other words, the basic building block of a neural network, the activation function plays two roles, and it kind of does them at the same time. So, number one is determine whether or not to fire. And what we mean by fire is transmit a non-zero output. So we think of an output of zero as being like not firing, the same way that, say, in a biological neuron, you simply wouldn't be transmitting information. If you transmit a zero, you're not really transmitting any information. Yeah, that's the idea. And then the second aspect is, if we are going to transmit a signal, determine what signal intensity to transmit. Okay. So if we do send out a signal, how strong should that signal be? And how can we control the strength of that signal? This is a part that we haven't really seen yet, because the perceptron examples we've already looked at, we were simply outputting a 0 or a 1. So there was no actual control of signal intensity. It was either fire or don't fire. All right, so here is a list, I'll put short in parentheses because there's lots of others. Okay. You might actually want to go take a, I mean, there's lots of places you can look. The Wikipedia article on activation functions has a good starting point for a larger list. There are plenty of articles online about it if you're interested in some of the other ones. But here's a short list of commonly used activation functions. first, which we've already encountered, although we didn't formally describe it this way, is what's called the binary step. So we define a function as follows. F of x will equal, and it's a piecewise defined function, 0 if x is less than 0, and 1 if x is greater than or equal to 0. It doesn't matter so much which one of these we put the equality part on. It doesn't really change the behavior all that much. I think the way we defined a perceptron before, a basic perceptron, it actually was the other way around, where its output is 0 if the net input was 0, but output of 1 if it was positive. But it doesn't really make a difference. Okay, so let's do a quick little graph of this. And all right, so what this function looks like, oops, let me put say 1 is right there. So if it is less than or equal, or if it's less than 0, if the input is negative, it's just 0. And then if the output is 0 or positive, non-negative, it is 1. Okay, so there's just a graph of the binary step function. So all right, a second possibility is that we simply, given a net input, a signal, we simply output the signal, whatever it is. And this can be accomplished using what's called the identity function. Okay, so the identity function is the function simply f of x equals x. Whatever the input is, that's also the output. And so the graph of the identity function is a 45-degree line through the origin. So for any input x, the y value is the same. Oops. Yeah. Okay. So it's this has the advantage, of course, of having a signal intensity, which the binary step doesn't really have. On the other hand, it does start to get a little weird to output negative signals, potentially. You have to kind of figure out what that means and so on. In some contexts, it might make sense. In other contexts, perhaps not so much. So they're kind of, like, in some sense, then, the disadvantage here is that the only not fire is if the signal is exactly 0. So what we want to do is combine together these two basic ideas, that the binary step has a fire not fire boundary, so to speak, and that the identity function transmits signal intensity. And to do that, we define what's called the rectified linear unit. RELU. Okay. RELU is defined as follows. F of x equals 0 if x is less than 0, and x if x is greater than or equal to 0. Okay. So the rectified linear unit, RELU, has a graph that looks like the following. Oops. Come on. So if x is less than 0, it's 0. Then if x is equal to 0, it's also 0. And then if x is positive, the y value is x. It's the 45-degree line again, y equals x. Okay. So in some sense, this combines together the ideas of the previous two. The binary step, which has the idea that it doesn't fire for a negative signal and fires for a positive signal. The identity function in the sense that it transmits an intensity for the positive signal. And the one advantage I didn't mention, but the identity function has over the binary step is that it's continuous, right? There's not a jump discontinuity. So the rectified linear unit has that property as well. There's no discontinuity now, it's 0. Okay. So RELU, as it turns out, is one of the most common activation functions. To use in the hidden layers. Okay. And that's because it incorporates both a fire, don't fire component, so in the hidden layers, the idea is you want the idea of don't fire to be there because you don't want necessarily kind of irrelevant or unimportant or useless information to be passing through the neural network. If at some kind of learning level, the neural network sort of evaluates some given data as not being important or useful or interesting, then it's good for it to not transmit that at all. Okay. Then it also has a signal intensity component. If it does decide that you're passing useful information, it can control how strong that information is. Okay. There's one issue here with using this. In a lot of respects, as simple as it is, it's very useful. It really does what we want it to do. But there is a kind of a potential problem. RELU, the function we defined above, is not differentiable at x equals 0. Okay, it's continuous there, but you've got that corner point, right? Kind of a hard change in the slope from being 0 to being 1. Okay, and why is that an issue? Oops, what happened there? Oh, as a result, there can be issues. There can be problems using it in gradient descent algorithms. So what we'll see on next week on Tuesday is that the way the neural network learns, take kind of the algorithm and how it evaluates its performance and updates itself, uses a gradient descent type algorithm. And so gradient descent uses derivatives. The gradient is kind of a vector of derivatives. So for this to work well, you want differentiability, smoothness. Because otherwise, if you run into a non-smooth point, that can cause problems. Okay. So one solution to this issue, I said one issue. Well, there's a solution for it. Introduce smoothness. Now, as it turns out, this problem is not that big, and the ReLU gets used a lot in the hidden layers, even though you do have this non-smoothness at zero kind of problem, because, well, it's only one point. Everywhere else is fine. The functions we're going to introduce for the smoothness are nice, but they're also more computationally complex. Okay, so that's, of course, a consideration that we have to keep in mind. All right, but nevertheless, at least for the theory, these are quite nice. So we're going to introduce what are called first what's called the sigmoid function, aka there's a bunch of other names for this, logistic, logit, or a soft step. Okay. And the kind of simplest form of the sigmoid function is as follows. Call it sigma of x. And sigma of x is going to equal 1 over 1 plus e to the negative x, where e is the natural exponential base. Okay. And so when we use this as the activation function of perceptron, it's often given a special name. So a perceptron using sigma of x as its activation function is often called a sigmoid neuron. Try to fix that a little bit. Okay. So what ends up happening is in a perceptron, so using the sigmoid function, the activation behavior is, well, one way you could kind of think about it. So how does it work? Is like, you might say, a smoothed binary step. Okay, So let's consider then the behavior of this thing, and so we can also observe the graph. Okay, so I'm going to kind of justify this claim. I'm going to make a few observations about how sigma of x behaves. So some observations. Well, sigma of 0 is a half. So here's this, just as a reminder, here's the formula for sigma. E to the 0 is 1, so you get 1 over 1 plus 1. Okay. Another basic observation we can make is that sigma of x is always positive. So no term in the formula for it can be is negative. Okay. The e to the negative x part is always greater than 0, and so then the whole thing is. Also, we'll talk in a moment about the behavior as x gets large, but basically the denominator can get big, so then this thing can certainly get close to 0, but it will always be positive. And it will always be less than 1, because it's always 1 over 1 plus some positive quantity. All right. So then what we want to do is make some observations about the asymptotic behavior of e to the negative x, and therefore sigma of x. So as x approaches positive infinity, e to the negative x, so you have e to a very large, an exponential to a very large negative power, that will go to 0. On the other hand, as x approaches negative infinity, then the negatives cancel out. E to the negative x is going to grow to infinity. Okay. It's going to become extremely large because you have e, the exponential base, raised to a very large positive power. Okay. So the consequence then is that as we approach positive infinity, go off to the right, the denominator approaches 1 over 1 plus 0, 1. As we approach negative infinity, go off to the left, we get 1 over 1 plus some extremely large quantity, right? Some quantity growing to positive infinity. So we have a fraction which is 1 over a larger and larger number, and so that approaches 0. So thus, sigma of x approaches 0 as x approaches negative infinity, and sigma of x approaches 1 as x approaches positive infinity. Okay, so now these observations are helpful for understanding why the graph of this function looks as it does, which we're about to draw here. So the graph is bounded between 0 and 1, and I'm going to draw a dotted line here where 1 is. Okay. So let's say there's 1, and then roughly I'll try to get halfway between. There's a half. All right. So we saw that the value at x equals 0 is a half. So that's where it crosses the y-axis. And then what you can observe, and this of course requires some more detailed analysis using the derivative and so on to consider the steepness, is that around 0 the graph is relatively steep. It's displaying roughly kind of exponential growth in both directions. But then it rapidly levels off. So it approaches 1 fairly quickly and then levels off there and then becomes asymptotic. So as we approach infinity, the value gets closer and closer to 1. And similarly, it drops down fairly quickly close to 0. And then, well, let me try to make that look a little better. And then becomes asymptotic along the x-axis as we approach negative infinity. So the idea is for values of x which are not too close to 0, it behaves a lot like a binary step. It outputs a signal which is almost 1 for positive and very close to 0 for negative. Now, closer to 0, that behavior, of course, breaks down. But and this is why it sort of smooths out, right? You're taking the binary step and you're kind of near in a little window around 0, you're smoothing it out. You're joining the two pieces together in a smooth way. All right, so if we can do that, we can make a smooth sort of binary step. You might ask, well, can we make a smooth rectified linear unit? Because that was the problem with the rectified linear unit, was this sort of lack of smoothness at a single point. Okay, well, what we do then is, the answer is yes, we introduce what we're going to call the sigmoid linear unit. SILU. And this is a very common activation function to use if you do care about smoothness everywhere, especially smoothness at 0. Okay. So the sigmoid linear unit is defined by f of x equals x times sigma of x. So you take the sigmoid function and multiply it by x. And what that looks like explicitly is x over 1 plus e to the negative x. Okay, so we can use the observations we just made about the sigmoid function to understand how this function f of x, the sigmoid linear unit, is behaving. Okay, so for large positive values of x, so we know that the denominator will be close to 1. So the entire thing is close to x. F of x is roughly x. So as long as x is reasonably large, this behaves like the identity function, so like the positive half of the rectified linear unit. Okay. Now, what if x is negative, okay, for large negative values of x? Okay. Well, then the exponential part is big, so the denominator is very large, right? The numerator is big too, but okay, this is one of those places where you kind of have to do some analysis. A large exponential is much, much bigger than just a large sort of value, a large number that you're using as the power of the exponential. This can be formally done using L'Hopital's rule to show that what happens as x gets large, in this case, is this entire quantity approaches 0. So for large negative values of x, f of x is going to be close to 0. Also, we can observe that it will be negative because the denominator is always positive. The exponential part will always be a positive number, whether it's big or small. So the numerator is controlling the sign. Okay. So f of x is going to be a small negative number. Okay. Also, we can make the following nice observation. F of 0 this time is equal to 0. So it passes through the origin in the same way that the rectified linear unit does. Since it's just 0 times sigma of 0, sigma of 0 is a half, but 0 times that gives us 0. Okay. So the idea now is we're going to smooth out the rectified linear unit in some sense. The output intensity is not quite the same, is not quite x, but it's close to it, and for positive values. And for negative values of x, it outputs a small negative signal, which and so not quite 0, but close. Okay, so let's take a look. Here's the graph. All right, so it passes through the origin, and then it has kind of a roughly, like a slightly exponential behavior that then levels off. Okay, so it's not quite a 45. In particular, it's below. Let me just kind of put the ruler. I'm not going to draw a line, but just for context. So there's where roughly where the 45-degree line would be. But it's kind of, oh, that's not going to work as well as I was hoping, because it'll think I want the ruler. Let me just put it right here. So it's going to be kind of below that for a bit, but then kind of, I made it a little too curved there. Yeah, that's close enough. Yeah. Something like that. Yeah. So that wasn't the best hand drawing I've done, but that's all right. Okay. So you can kind of get an idea that it's kind of becoming asymptotic to the 45-degree line. Okay, that's what I was trying to draw at least. I didn't do the best of it, but you get the idea. It's not quite there near zero. So then below zero, it becomes negative. It has an absolute minimum. And then, as indicated, it becomes asymptotic to the x-axis. It approaches zero, and it's on the negative side. Okay. So you might ask, how bad does it get in terms of being negative? So this point here, the absolute minimum, is approximately negative 1.3 in the x direction and negative 0.3 in the y direction. So it never gets that big in size, right? Negative 0.3 is the most negative signal you would output. So then it does, in some sense, then do what you want it to do, which is be a sort of a smoothed out version of the rectified linear unit. So notice, so what we're trying to do is we're trying to take this function here and smooth it out at zero in a kind of a systematic way, and that's what we've basically accomplished. Okay. So if that's an important consideration, then this function works very well. Okay, we'll make some comments about these in a moment and talk a little bit about the sigmoid neuron idea. But first, let's introduce one more activation function, or kind of a class of them, that are useful. Every kind of activation function so far that we've talked about, even though we didn't say it, is kind of implicitly a regression activation function, right? You're trying to output a signal. The binary step can be used in any way you want, but for either kind. But all these ones where we're trying to output a signal intensity, X or some variation on it, clearly we've got kind of a regression type problem in mind. Okay. So for classification, especially multinomial classification, we want to introduce a group of functions called softmax functions. Just a little bit of notation here. The whole idea is these are going to be very useful for multinomial classification, where you have many potential target classes. So let's make a vector, call it a vector x, and x will simply consist of, say, x1, x2, some number of entries, however many we need. Let's say xr. Okay. So then for every choice of j between 1 and r, define a function so we'll have a bunch of individual functions, call it f sub j, and what does f sub j do to the target vector x? It computes e to the x sub j, so the exponential with whatever the jth entry is as its exponent, over the sum of all of them. Of the e's. So the sum from j equals 1 to r of e to the x sub j. Let's use different, actually, let's say I, so that I'm not using the same index as a fixed thing and then for the summation. Okay. So in some sense, it's like a weighted exponential sum. Okay. And it's worth pointing out that these functions, these are all differentiable. Okay. And so I'll point this out. As mentioned, softmax is useful for multinomial classification problems. In particular, where what you're trying to output is a class probability, right? So you're trying to make a prediction of whether or not, or what probability is it that some data point you're predicting is in a certain target class. Okay, so for that to be the case, if that's the way we want to use this, it should be the case that the sum of all the class probabilities adds up to 1. So it's worth making the following note to see that this does what we want it to do. Okay, so suppose we add up all of these functions, take the sum from j equals 1 to r, f sub j of x bar, or of x, yeah. Okay, so that is the sum from j equals 1 to r of e to the x sub j over the sum from I equals 1 to r e to the x sub I. Okay, and so now we're just going to play around with some summation notation. This is equal to the sum in the denominator is indexed over I, right? So as far as the j part goes, the indexing over j, let me just fix this a little bit, make it look a little nicer. As far as the indexing over j goes, the sum in the denominator is a constant. So I can just pull it out. So what I've got is 1 over the sum from I equals 1 to r, e to the x sub I, and then times the sum from j equals 1 to r, e to the x sub j. Okay, but now we make the observation that those two sums are the same thing. One of them is indexed over I, and the other is indexed over j, but they're exactly the same expression. So what we end up with is a certain sum divided by itself, and so this is equal to 1. Okay. And so what this means is that the total probability over all the classes is 1, which of course we need that to be the case. If we're predicting probabilities, the total probability must equal 1 for a probability distribution. Okay, so that just checks that sort of softmax does what we would want it to do, okay, when used in this way. All right, so let's just make some comments about the activation functions that we've talked about so far. Some of this we've already kind of remarked on as we went through. We'll write some of it down now. Okay, what are some common activation function conventions for outputs? So we often use a different choice of activation function in the output layer than in the hidden layer. Well, one is that just to use linear activation, f of x equals x for regression problems. So in other words, just output at the end, when you're at the output layer and you put out all the signal together, just output whatever the signal is. Okay, and this makes sense in particular. With a regression problem, it may make a lot of sense to output a negative value. Right? It's perfectly reasonable. Like if your algorithm is predicting, say, like the value of something, I don't know. Let's say you're predicting, I don't know, some kind of value thing, right? It could be negative, right? You could lose money. That's not impossible, obviously, right? So having negative outputs makes sense at that step. Then it's very common to use the sigmoid function, sigma x equals 1 over 1 plus e to the negative x, for binary classification problems. So in a binary classification problem, let's say you're predicting you're gonna predict the value of say of a true or a one or whatever. Okay. So then the probability of that. The other probability, of course, is just one minus that. So you only need one activation function. And the sigmoid function works as a probability because it's between 0 and 1. So it will predict the probability of being in a class. And then the probability of the other class is just 1 minus that. And then we, as already described above, we use the softmax family of functions for multinomial classification problems. And in all three cases, then, your output activation function is differentiable. Right? F of x equals x, the identity function certainly is. The sigmoid function is. This is why you'd want to why sigmoid is useful rather than using the binary step for binary classification. Also because what you're predicting when you're using sigmoid is a probability, right? And a probability should be between 0 and 1, but you don't want your predictions to always be 100% or 0%, right? So then using sigmoid allows you to have kind of a continuous probability range. Okay, so let's go back to the question of why at the hidden layers would we want to use something like the rectified linear unit or the sigmoid linear unit, replacing it with a smooth one. Okay. So why RELU for the hidden layers? Okay. So consider then what RELU is doing, right? So if it outputs a 0, that's just saying don't fire. And if it outputs an x, a positive value x, it's saying fire, and with this particular with this signal intensity. So whatever your net input is at that step, just fire that out, right, as the signal. Okay. So this setup is simple. It's intuitive. It works for many setups, even most setups. It's continuous. And it's as part of sort of being simple and intuitive, it's computationally efficient. There isn't much additional computation to do other than the net input's already been computed, and so all we're doing then is just doing a comparison. Is the net input positive or negative? And then if it's negative, we output a 0. If it's positive, we just output whatever the net input is. Okay. So there's no actual additional sort of mathematical computation going on. Okay. Right? So then why would we want to consider, say, sigmoid neurons? So we have a nice simple framework. Why would we want to kind of complicate it with this kind of exponential logistic type function or x multiplied by it? Okay. So the comments I'm going to make here are basically related to going from the binary step to the sigmoid function, but the same applies going from, say, the rectified linear unit to the sigmoid linear unit. So when I say why sigmoid neurons, so in other words, or expanding on what that means, why replace the very simple binary step function with the more complicated sigma of x logistic type function, right? 1 over 1 plus e to the negative x. So and then similarly for RELU, going from this rectified linear unit to the sigmoid linear unit. You're replacing a relatively simple function. Did I remember to call this SILU above? I don't remember. Yeah, I did. Okay. So here we're replacing this rectified linear unit, which is quite simple, just 0 and then x, with something much more complicated. So you've got this sigmoid function multiplied by x. Now, and if you think about it computationally, there's a lot more work here, right? Because you're computing. First of all, you're computing an exponential, which takes some computing power, because it's a transcendental function. So of course, it's an approximation. But then you're doing a sum and a quotient, and maybe a product if you have the SILU as well. So there's a lot more going on in terms of computational steps, including a more complicated function in the steps. Okay. All right. So then the answer is the answer to the question in some sense is the answer in both cases is to smooth out the more basic perceptron. You get more control from smoothness than you do just from straight up continuity. Okay. Let's take a look at a little bit. Well, let's look at the mathematics of this a little bit. Okay. So consider the net input, okay, which we've defined. We'll use the same notation we've used before. So W dot X. So we have our vector of weights and our vector of inputs, and then plus B, the bias or threshold. Yeah. All right. What happens if we apply the sigmoid function to that? And so we use that quantity as our input for sigma of X. So that's equal to 1 over 1 plus e to the negative of that. So negative W dot X minus B. Right? So the negative of the whole thing. Okay. Let's just give that a name, just to make some notation a little bit easier. Let's say that Z is that quantity, or is W dot X plus B. Okay, so some of the observations we've already made are that if Z is very large, so I'm just going to say like much bigger than 0, then e to the negative Z is close to 0. And so then what does that tell us? That tells us that sigma of Z is close to 1. Okay. So what we're saying here is for a large net input, this outputs a signal very close to 1. So the same thing the binary step would do. And if Z is negative, or large negative, then e to the negative Z, as we know, is very large. It approaches infinity. And so sigma of Z is close to 0. Okay. So it's producing a don't fire just like the binary step would. Now, the whole point then is what's interesting then is what's going on in between. So for Z, say not too large, in either direction, right? Sigma of z, the value here, produces a more subtle signal than just 0, so don't fire, or 1, fire, right? So you're getting some value in between. In particular, you can think about it as a probability. Okay, and that actually doesn't say all that much. I mean, most of that's just a repetition of what we already saw about how this sigmoid function behaves mathematically, right? And in particular, all of that would apply if this thing was just continuous rather than differentiable. So the smooth, nothing I've said here really is actually employing the smoothness yet. Okay, but let's see how that matters. Okay. What the smoothness allows us to do is essentially control the changes. We can describe how big they are, how they vary as the weights and bias change. And that's important because the weights and bias changing is what's going to happen algorithmically as the neural network learns, as it trains itself on the data. Okay. The basic point is this: small changes in, say, delta Wj, we use delta to kind of indicate change in the weights. And say delta V in the bias. Produce a small change say delta output, call it, in the output predictions of the sigmoid neuron. All right. Okay, so first let's take a look, just kind of like a graphic, an illustration of this. But then we're still nothing I've actually said there in words. Even if it's kind of imprecise, but nothing there would apply or doesn't apply if it was only continuous. Okay. The big thing we're going to get from smoothness is we're going to actually be able to write down this relationship in a moment. But let's just see it first, what's going on. So this is the kind of the idea graphically. Okay. So if you take your weights and you add some kind of small change to all of them, then you simply add a small change to the output you already had. Okay. So this is the idea. And that at least is coming from continuity, right? So small changes in all of the inputs produce a small change in the output because of the continuity. What we get from the smoothness is we can actually measure the size of that change. And with continuity, that's harder to control. Okay. So in this case, the change in the output is approximately given by summing over all possibilities of the partial derivative of the output with respect to each weight times the change in the weights, plus the same thing for the bias, the partial derivative of the output with respect to the bias times the change in the bias. Okay. Now, so if you're not super duper familiar with the partial derivative notation and so on, don't worry too much about that. Here's the observation you want to make. Since sigma is differentiable, the partial derivative terms exist and are finite. So what that tells us is that the change in output. So in other words, those symbols there you can think of them then just as coefficients, right? They're just constant or scalars for certain values. What this tells us is that the change in output varies approximately linearly. So it's very controllable, right? If the change is linear, it's very easy to see then how it changes as we make slight incremental changes in the weights and the bias. So it varies approximately linearly with the change in the weights and the change in the bias. Okay, so that's what we mean by we can control the sizes of the change, right? So those are just linear coefficients, and then the weight delta Wj and delta B are both linear terms as well. So this is just a linear combination of the changes in the weights and the change in the bias with various coefficients, and those coefficients come from values of the partial derivatives. So that's nice in certain kind of computational ways that you have this level of control over what's going on. Okay. What we will see next time is why this matters is because we're going to use a gradient descent algorithm in the learning process, in some sense, in the algorithmic process of training the neural network. And then the smoothness, in some sense, guarantees that as the weights and bias are being tuned, right, and they're changing, then you don't get big jump changes in the outputs. That's kind of what we're trying to avoid. And we'll use the MNIST. Use the MNIST example to describe how that might happen, and then how we're avoiding it. So that's what we're going to talk about on Tuesday. Is what's called backpropagation, which is the sort of mathematical algorithm underpinning the neural network learning structure. And that's where we'll pick up next week. And just a quick reminder that tomorrow is the sort of formal assignment date for the assignment 4, which is a neural network assignment. It's just playing around with the neural net package in R and seeing the effect of adding more hidden layers, adding more nodes at each layer, and both, and kind of how that affects the network. You'll also get to see kind of how R does some basic outputs of what a neural network looks like. So take a look at that. Also, do remember that at least officially the project outline is due tomorrow. If you do need a little bit of extra time on that, just let me know. And so that's it. And if not, I will see you guys next week.